Hi, welcome to solveandgo.com. This is another example of auxiliary equations with repeated roots. This example shows why we have the given form of solutions of second order differential equations with repeated roots. So the form you see in the textbook. Okay, so here's the setup. We have a differential equation, a times y double prime plus b times y prime plus cy is 0. And the auxiliary equation has roots. So the auxiliary equation is a times r squared plus br plus c is 0. And suppose this has roots r1 equals r2. Now suppose for a minute, not equal to r2. Suppose for a minute that the roots are not equal. So the first thing we're told to do is show that theta of t, which is e to the r2t minus e to the r1t divided by r2 minus r1 is a solution to the differential equation above. Okay, so this particular solution is chosen for a very specific reason, and we'll see what this is in a minute. But let's first check that this is indeed a solution to the equation. Okay, so here is theta. Let's find its derivatives. So theta prime of t is r2 e to the r2t minus r1 e to the r1t over r2 minus r1. Okay, so what is theta double prime? It is going to be r2 squared e to the r2t minus r1 squared e to the r1t. Now I'm going to have to erase theta for a minute. Divided by r2 minus r1. Okay, so let's plug everything in. What we get, you can copy these down if you like. I'm going to erase them and plug them into the differential equation above. What we end up getting is a times r2 squared e to the r2t minus r1 squared e to the r2t divided by r2 minus r1 plus b times r2 e to the r2t minus r1 e to the r1t divided by r2 minus r1 plus c times our original function theta, which is this. That's a t minus e to the r1t divided by r2 minus r1. And this we can rewrite as follows. Okay, so again, I'm going to have to erase what we have here. Pause and copy this down if you need to. What we end up with is the following. So we end up with a r2 squared minus plus b r1 plus c times e to the r2t divided by r2 minus r1, and then minus a r1 squared plus b r1 plus c times e to the r1t divided by r2 minus r1. And because r1 and r2 were assumed to be solutions to the equation, sorry, this is an r2 here. Okay, everything looks good. These factors in front of e to the t are both 0. Okay, because of our assumption that these r1 and r2 were roots to the auxiliary equation. Okay, so this whole thing equals 0, and indeed theta of t is a solution. Okay, so we assumed that r1 and r2 were different. So let's take a look at theta again. t was equal to e to the r2t minus e to the r1t divided by r2 minus r1. So r1 and r2 are different, so that we don't get a 0 in the denominator here. But what happens when they're equal? Well, to figure out a solution in that case, we can't simply set r2 equal to r1, because as you see, we get 0 over 0. But we can take the limit. So let's fix r1 as a constant, for instance, and take the limit as r2 approaches r1. So the limit as the roots are becoming equal of these solutions, and see what we get. So r2t minus e to the r1t divided by r2 minus r1. So plugging in r2 equals r1, we get 0 over 0. This is an indeterminate form, so we can take the derivative. So we take, using according to L'Hopital's rule. So this is the limit as r2 approaches r1 of the derivative of the top with respect to r2, because that's the variable that's changing in the limit, divided by the derivative of the bottom with respect to r2. So the derivative of the top with respect to r2 is going to be t times e to the r2t. That's the derivative of this factor here with respect to r2. This second factor term here has no occurrence of r2, so its derivative is 0 with respect to r2. And then we divide by the derivative of the bottom with respect to r2, which is 1 minus 0. Again, r1 is fixed as a constant, so its derivative with respect to r2 is 0. So we get that. And then we find that this limit is t times e to the r1t. Okay? So if r1 equals r2, we see that this is a solution, and so is our usual solution. Then e to the r1t and t e to the r1t are solutions to the, let me squeeze that in here, are solutions to the differential equation above. Okay, so this is one way of showing that these two are actually solutions to the equation.